clouds. We care about all microphysics and all dynamics. Dynamics are very important. EarthCARE is the first satellite that is expected to do something about dynamics. But if I had to put a list of things, we do fundamental research in all sorts of clouds for many years. We're using ARM observations, ground-based observations, spatial observations, airborne observations, sea-based observations, all sorts of simulators. We're very interested lately in what we call how to do actually experimentation to be efficient. I mean, not just to do the collection of the data, but the observations being made with a purpose. This is a little bit different. It's not I go out and I deploy, then I go back to my office and I try to understand what exactly I measure. This is where the observations are being informed by the model needs before the event observations take place. Okay, so this requires that all this becomes in the virtual. You do it digitally. Doing things on the digital is free. You just need a computer. Doing things in reality and going to Ambikitra with a ferry boat on maintaining the instrumentation, you all know is very difficult. So this is the kind of things we haven't done very often, which is basically think before we actually do observation. Very hard about what observations will be done. Sometimes observations cannot have the information for whatever you want to study. Sometimes we even ignore that. We do observations, we see something, and immediately we think that we can actually constrain a process. That's far more difficult. And we work, of course, as here with industry and a lot of cool sensors and things that you can find in the US. So when it comes to radar, the US is really very advanced compared to every other location. Now, we talk about EarthCARE, but EarthCARE is not the only game in town. This guy here, Alessandro, he has been involved in many, and myself. EarthCARE is on the top. It's launched in 24. Hopefully, we'll go to 28. But, you know, a private company show up in 2020, 2019, I think. They make a tremendous announcement that they said they're going to launch 20 radars in space by 2025. Guess what? They have already 2, the Pathfinders. They are launching the first real one in the summer, and by the end of next year, they will have 20 in space. Now, all the agencies of this planet, JAXA, NASA, ESA, ISRO, the Indian Space Agency, whatever you want to put, the French, the Greek Space Agency, altogether have launched 5 in the last 30 years. Private sector comes because there's money in weather prediction. It can launch 30 in 5 years. Okay, so this is an incredible forward-looking idea. So things that you thought cannot be done, all can be done. There's a NASA mission which is focused on investigation of cumulus updrafts. So looking in dynamics, which is going to be launched in 2026. Big AOS mission in the US has a launch in 2028 of the PMM, which is precipitation measurement mission. And there's a cloud opportunity that will probably launch 23, 24. These are all radars. EarthCARE, though, is very special, very special. So now I'm going to focus on the EarthCARE, very high level. Please stop me if you have any question about EarthCARE. All right, so EarthCARE launch, there's excitement and a lot of nervousness because we are looking at the data. We can't talk about the data and we can't show you data. There is a boycott and we cannot really show you results from the radar. But I can tell you that the radar data are spectacular, are exactly what we expected and more. So there's a lot of excitement, but there is a few wrinkles we need to iron and before we get out of the commissioning phase, which is expected to be at the end of November. So when they put together the EarthCARE mission, it was called the 10 watts per square meter mission. They said you're going to fly with a LiDAR, measure aerosol and cloud location. Fly with a radar, sees the interior of the clouds. Fly with a multispectral imager, get visible IR. And in that box, you have this very nice cut of the radar LiDAR and some kind of 150-kilometer box with MSI. We're going to do the transfer and we're going to match what the broadband radiometer say in space, what's happening in the box. If you have done good retrievals, you should be able to reproduce it. So it was called back in the days the 10 watts per square meter maximum differences between what we think is happening with actually measure from space. This ended up not being the goal in the end. It ended up being much more difficult than we thought. Nevertheless, EarthCARE, it is a very ambitious mission. So there are some cool things. First of all, first time measurements of motion, much superior LiDAR, HSRL, high spectral resolution LiDAR. I have to explain that to this group. And better sensitivity, better resolution, we can go into that. But before EarthCARE, there was something else, which is actually a driver, a motivation for that care. It was the NASA A train. Have you guys heard about the NASA A train? Fine. So NASA A train was a different concept. It was not put together as a train. There was not a mega proposal that said we have to fly 6, 7 sensors on a constellation. It happened with time. There was one explorer there, the next explorer, same altitude. They put them together. They start building together this constellation. We all understand this power of synergy. Different sensors from microwave to optical, passive, active, they all provide different pieces of the information. So the NASA put that together from 2006 with the launch of CloudSat and Calypso, and still goes. Some of these sensors still goes. CloudSat went for what, Alessandro? 17 years, something like that. It was like, once you fly something in space, typically runs very well. Transformative data, first time having vertical cut of clouds. You can see that there is cloud at the top, cloud at the bottom, cloud at the middle. 3 layers, 1 layer, 2 layers. Things that we could not see before. Very important mission. So what's the difference between this mission and EarthCARE? That's the question. It's not rhetorical, I'm expecting feedback.
The collocation of the material sensitivity.
The collocation, they have collocation too.
Then even better.
So you think that, so there's an argument here, the EarthCARE, just to pivot in the next slide anyway, it's all together in the same sensor. Is that an advantage or a disadvantage? What do you guys think? I mean, we know because we went through that. It's advanced, but when you go to Antikythera, you don't put the LiDAR and Antikythera, the radar in the observatory here. You want to have them collocated. You want to be looking at the same sampling volume of the sky, correct? So there's a great advantage to put the sensors together. You don't have to have do the flight dynamics and figure out all the satellites together for one phase. What do we do? So it's a great advantage. But what do you see about the satellite? Huge weight, okay? More than 2 tons, okay? Tremendous amount of power, 2 kilowatts. You know how much a microwave oven? Anybody has microwave ovens in their houses? This is not a thing we do in Greece, because in Greece we don't use microwave ovens to create food. But the microwave oven is probably like 800 watts, correct? So we run EarthCARE, we need about 2.5, 3 microwave ovens. That's it. Well, this kind of power doesn't exist in space. We don't have power to run 3 microwave ovens non-stop in space. So it requires this very long solar array and even bigger batteries to store the energy when you are in the dark side, when you don't have the solar. So this ends up being a very big satellite. The other thing, Eleni, these all satellites are transformative, okay? The HSRL is a new technology. The Doppler in space is a new technology. If one of the 2 technologies, if there was a technology maturation issue, that means we could not actually do we're confident that this is the LiDAR or the radar, you have to wait 4 years to fix the trouble. So there was a delay of 4 years just because of the radar. There was a delay of 4 years just for the LiDAR. But because they're together, that makes like a bundle of 8 years. If they were separated, you could fly the radar, fly the LiDAR in a different time. So if you have many sensors together in the same satellite, you are bound together that everything has to be totally what they call the TRL, technology readiness level, at the highest possible, no risk, and then you fly. So part of the delays of EarthCARE had to do with the fact that we have back-to-back, not in parallel, technical issues which delay the satellite, all right? So altitude very low, 400 kilometers. Anybody knows the altitude that the A-train, NASA A-train was flying? 700. So what would be the advantage of doing, why we didn't do 700? What would be the advantage of being at 700 versus being at 400?
They could come faster and they could last longer.
They could last longer, much less friction. You add 700, you just pretty much the lifetime of the mission could be 20 years. All you care is that the sensor operates. At 400, you don't have this luxury. At 400, typically you have to use all your fuel just to adjust, and you might have 3, maybe 4 years of mission. Okay, but why would do that? Why would we wait for 24 years and then put a satellite which only is going to last for 3 years? Why do you think they selected to do the non-obvious option of going at 400 and not go at 700 so we can have EarthCARE until 2045? High resolution, high sensitivity. The closer you are, the high resolution, the high sensitivity. Okay, so we think that the resolution and sensitivity is really the new thing, plus the two big measurements, high spectral resolution LiDAR and the Doppler quality. Okay, so we want to do the next thing. The next thing in modeling is resolution. The next thing in observations is the resolution. It's always been like that. That's the most transformative thing. All right. So I'm a radar guy. I would do radar. So the radar is the thing you probably care. You are making the most spectacular images, correct? So what do you know about radar? It says that this is the most sensitive radar in space, minus 35 dBz. What that means? Have you a visual what that means? What this minus 35 dBz means? Okay.
That we're not able to be the report.
Okay, so you have a number in mind. So if you know how much will have to be the dBz if you need to get an umbrella, you have that mentally connected. What is the dBz when actually you go out and you need an umbrella? This is how you be calibrating the new weather radars that Greece is going to get. That would be a very clever way. What would be the dBz value if you go out and not just you get drizzle in your face, but you actually think that you have to have an umbrella? Minus 20, minus 5, plus 50. Any sense what the dBz scale of values is? Eleni? Lucas?
Not 35.
Okay, what would be the value?
5.
5. Okay, so I would say for this frequency, plus 5. At plus 5, if you see from space plus 5, and it's close to the ground, it's a lot of rain falling. Depends on the temperature, it's going to be snow or rain. But that's the first thing. The beautiful thing about radar, which mostly is that it penetrates, correct? Microwave would penetrate, LiDAR would not go. What do you think the radar LiDAR would do for cloud research? A lot of you want to do secondary ice production, you want to do ice microphysics. So what the LiDAR would give me if I want to do cloud microphysics that the radar cannot give me? You have a sense, this is synergy now, correct? I do all this burden to put the radar and LiDAR together. There must be a reason for it. And it's not just about mapping, that the LiDAR sees aerosols and the thin clouds and the radar sees the heavy stuff, the thick, optically thick things. When I have them together and they're both looking at the same cloud, the same precipitation, what can I learn by, is there anything actually I can learn by combining the radar and LiDAR?
But the radar can see the layers and the small crystals.
Very small crystals. Okay. So you understand that, correct? The LiDAR goes with the second power, but the LiDAR doesn't penetrate all the time, correct? And what can I do if the LiDAR detects the supercool liquid? We have seen that from Klaus and Calypso. There's some examples, these thin layers at the top of ice, because you can see, oh, this is bright echo. There must be definitely liquid droplets, correct? Very strong reflection. But in reality, if you look how we use it microphysically, we don't use it. Meaning, when we give you a retrieval, an estimate of how much water is in the atmosphere, or how much ice particles are, or how big are the ice particles, we don't use that. Somebody who does a correlative study, for example, can I see how big the particles from the radar look if I have or don't have supercool liquid layer? I might use it, but that would be after the fact. In the retrieval, it's not used. There's very little, correct? There's very little information I can get from quantitative. The backscatter of the LiDAR is not really used quantitatively, except now with Robin Hogan and Shannon, they use a little bit on the top of the cirrus layers. So there's not really too much synergy when they overlap. There's a lot of complementarity. That here. Look at this image. The top image is, first of all, Clauset, and this is the better thing with EarthCARE. So the EarthCARE will see even more this, what Eleni was saying, the thin cirrus. You will see this super cool liquid layer over there, much better in the right part of the image. And the new measurement that everybody's excited is the Doppler. It looks very noisy, correct? This looks very noisy, the last panel. But that's the exciting thing. That's the first time we're going to measure Doppler from space. All right? You guys know, you know what Doppler is? Have you looked at Doppler measurements? Who has looked here, Eleni, Doppler radar data?
We don't have a master students. I suggest you say what master.
Okay, I have one sentence. Okay. So that's we went up the BAMS article back in 2015 explaining the EarthCARE mission. We had to show. There's a lot of anxiety to demonstrate that you were better than Clauset. So here you saw Clauset, and this is how EarthCARE. And this is the Doppler. I made this plot for the Doppler. It looks a little noisy. What do you see in the Doppler? Things are falling. Everything which is positive falls towards the ground. You see at the top, very low value. This is ice falling. Falling. What's the typical fall speed of ice particles? Second. I give you a pass on this because you don't get a lot of snow there. And how fast the raindrops are falling? More.
On the side.
And if you follow Alessandro's, for those who follow Alessandro's tutorials, they must know that this radar, the W band, we see raindrops, although the raindrops naturally can fall up to 8-9 meters per second as surface conditions, the Doppler velocity recorded by this radar will not exceed 6. If you're using a weather radar, you will match the 9. Okay, anybody knows why is that? Why this radar, the W band, is 94 gigahertz, will look at the Doppler velocity, will measure up to 6. And if I had a different radar, which is like a operational radar, and look in the same exactly cloud, it will measure a velocity of 9. Can anybody think why? How is possible? Just before I change the sensor, the Doppler velocity is not the same, basically indicating that the drops are not falling the same. Is that even possible? Write down attenuation. Write down, Alessandro. Go ahead. Put there. A, attenuation. We're going to do a quiz here. We're going to see who's going to go there. A, attenuation. That's valid. Attenuation, basically, Eleni says, because if you have a weather radar, the weather radar has a one key feature. It can go through weather, meaning it has almost negligible attenuation. So if you have a weather radar on the top of this image, looking down, you go through the whole material of the cloud and the rain, it's almost like a see-through material. I don't even see it. So because I don't have attenuation, the raindrops go faster. Where the other one is attenuating and the raindrops go slower. Any other thoughts? They are the same rain droplets in the volume. They are the same exact rain drops. This is exactly what you see. Just to help the image. This is the image. The radar looks the same raindrops, the same volume, what you see within this cylinder, the white cylinder, the outline. Both radar, two radars, but at different operating frequency. Why this group in particular has such a great appetite? Really, you guys are unique. Appetite on building the most exquisite LiDAR systems. Why Eleni wants 3 lambda systems? What the different lambdas give you, Eleni?
Same.
So, yes, so the same logic. Although it's exactly the same particles, the wavelength I use allows me to see different part of the spectrum. The wavelength responds more to different part of the spectrum of the particles. So when you put, Alessandro saw what is, Alessandro will show you that, and we don't have this video to show Alessandro what he's doing, but, keep talking. I might find a way to steer the camera. You can steer the camera, this one, correct? There's a camera here. Yeah, you should do that. Joanna, can you do that? Can you turn it? So this is very important, correct? Because you do calibration and you use a weather radar picking up and you see the raindrops falling 9 meters per second. Don't call me exotic hours in the US. You tell me that the raindrops in Antikythera fall 3 meters per second than the W band. Right? This is why we do this workshop. To make sure to understand that although they are the same answer, they just look at different things. Now I can see you. You can go ahead. Bring the whiteboard closer. So now Alessandro is going to explain to you. This is a very simple part, but this is where I end my presentation, correct? Let's talk just about that. Why the Doppler from EarthCARE is not necessarily the same Doppler velocity you get with the radars you're going to put in Pangea. It's not going to be the same exact value. And that has nothing to do with the satellite jumping up and down or moving too fast. And then after that, Alessandro can take off on his presentation. I'm done with that. And let's do this. Alessandro will do it. By the way, I will introduce Alessandro. I've known Alessandro since 2007. We jumped together in EarthCARE. I can tell you for sure, he's the best known, it's an honor to have you, the best known radio transfer micro, period. And when I say period, because I work in the US, I know how good scientists they have in NASA different centers, but every major challenge, new idea, is going to come from this guy. So Now he's going to tell you, he wears also the EarthCARE t-shirt, so he's ready for that.
Okay, so
here now,
but this will
for the same particle size distribution, you can get different Doppler velocities.
because the Doppler velocity is a reflectivity weighted measurement. So take in your volume, you have different droplets with different sizes. So each one of them, when you do a Doppler measurement, counts with its backscattering cross-section. So now, if you take radars with different wavelengths, backscattering cross-sections are different. Okay? So if you have a radar like the meteorological radar, typically all raindrops are in what we call the Rayleigh regime. Okay? So the backscattering cross-section is proportional to the B6, so to the size of the dimension, and is inversely proportional to the fourth power of the wavelength. It's exactly the same as in Aerosol, right, and LiDAR systems. You have, if the dimension of the scatter is much smaller than the wavelengths, you are in Rayleigh approximation. Now, what happens when you have 94 gigahertz? 94 gigahertz is 3 millimeters. So this means that droplets of the order of 1, 2, 3 millimeters, like typical droplets, like typical raindrops, are not in Rayleigh approximation. So this means what? It means that, well, if you know what happens when you go out from the Rayleigh approximation, the backscattering cross-section starts doing those kind of oscillations. So you enter what we call the non-Rayleigh regime. Okay? Somebody used the word me regime. I think me is explaining, me theory is explaining everything. Actually, I prefer to use the word non-Rayleigh regime. So you start having the backscattering cross-section, instead of steadily increasing with this d to the power of 6, they start doing oscillation. So this means that the larger raindrops, they have smaller backscattering cross-section, if normalized to lambda to the fourth, compared at the shorter wavelengths like 94 gigahertz of EarthCARE, than radars like 3 gigahertz, 6 gigahertz, 10 gigahertz. So this means that the large particle, they weigh less. With respect, I mean, you have always to do the comparison with respect to the long wavelength radars, right? So in your population, you have a lot of particles. So you think about, you have a radar from the meteorological services, right? You have all your particles, and each one of them weighs with the radar backscattering cross-section. Now, this means that the large one, they will weigh a lot if you have if you have the radar from the meteorological service. Now, if you go to 94 gigahertz, so of course, the large particles are the ones that are falling faster. So this means that you will weight more the part of the spectrum with large falling speed. Now, if you go to 94, the relative weight of the larger particles will decrease. And this means that you will weight more the part of the spectrum of the small particles, which are the ones that are falling slower. Okay, that's why you see this reduction in the mean Doppler velocity, because the mean Doppler velocity is always a reflectivity weighted, a cross-section, a backscattering cross-section weighted. What counts is, although you have a lot of billions of particles in your backscattering volume, and each one of them counts with the backscattering cross-section. Okay, so you see this reduction. In fact, actually, we have techniques that actually use this dual, the difference between this velocity in principle, to actually get an estimate of the size, the characteristic size of the drop size distribution. Okay, so this is why, for instance, we suggested that we should use, for instance, or in ground-based instrument, arm facilities or accuracy facilities, we have multi-wavelength radars, right? And some of the technique to retrieve the characteristic size of the raindrops is indeed looking at dual Doppler. You look at the difference between the Doppler you measure in one frequency and the other, and there is a difference, of course, if the particles goes out from Rayleigh. So if the particle starts being large, okay, compared to the wavelengths, and you start seeing this, and actually that difference in the velocity is an indication of the size or the characteristic size, the mean Doppler diameter of your drop size distribution. Okay, so in 94 gigahertz, indeed, you see this reduction because, as I said, 3 millimeters becomes really comparable with the size of the raindrops.
You can start now with that. I think it's better if you have the presentation there so you don't sit in front of the screen. That's
yes. Okay. So today I will discuss another topic, but I will immediately see how this links with one, which is this Wyman mission, which is a candidate mission in the European Space Agency EarthCARE 11 program. And this mission will measure global in-cloud winds, clouds and precipitation. So, but basically, just to keep going with the story, yes, I met Pavlos basically in 2008. At that time, actually, I was in Bonn, and we started actually working on EarthCARE. And I remember I was working essentially on the simulation of the Doppler. And yes, we started with the NISA project, and then basically in the years afterwards, we did a lot of studies. We looked at pointing issues. So we wrote several papers. At a certain point, because they were only saying the launch will be in 2 years, the launch will be 3 years. So I thought, well, okay, I will start really working at this thing seriously when I will see that the launch is 18 months. Actually, indeed, when you see that the launch date is 18 months, then you are sure that you will launch the mission. Because essentially, at that stage, you basically are sure that the mission will start because it means that all the instruments are ready and they start basically the standard procedures. When you arrive at 18 months, you are sure that you will launch essentially. But at that time, you say, okay, let's think about something else. And in fact, we were thinking at other things, other ideas for future missions. And in fact, at this stage, I remember we wrote together a paper on polarization diversity. So we were actually thinking at the Doppler as it was envisaged for EarthCARE, and we were already thinking, well, we didn't do anything because we were not in the initial project, right? It was Anthony and then the Japanese. We were just thinking, is that the right way to do the Doppler, or it will be noisy, or we'll have problems, right? At that time, I was thinking, well, for convection, for instance, well, there will be a problem. Because you have seen the image, the image that Pavlos showed is an image which is noisy, first of all, right? It's noisy. The second thing, in the color bar that you have seen for the Doppler, the color bar basically goes from -5 to 5 meters per second, -6 to 6 meters per second. So there is, in Doppler radars, there is a problem which is called the Nyquist problem. Okay? So because in Doppler, when you do Doppler with the radar, you measure a phase. A phase by definition is an ambiguity. Okay? But by definition, you convert a phase into a velocity. You know that you have an ambiguity, 2 pi ambiguity in the phases, right? If you measure 2 pi, 4 pi, 6 pi, it's the same thing. It's a phase. Okay? The phase is a 2 pi, has a 2 pi periodicity. So this means that everything falls back into a Nyquist interval. And the Nyquist interval for EarthCARE is of the order of, depends a little bit on a parameter which is called the pulse repetition frequency. It's of the order of ±5 meters per second. Indeed, it's good because if you want to measure the classical velocity that we have seen, sedimentation velocity of ice, yes, is 1 meter per second, so it's fine. Droplets, 3-4 meters per second is fine. But of course, if you want to really look at deep convection, then you may end up in trouble, okay? Okay, so there are other issues, but anyhow, so we were thinking, well, can we do something else? So I can, well, people back in the days have already thought a lot of things, and there is another way to do the Doppler, which is called polarization diversity, which has the advantage that essentially, so that the problem of the, essentially, the problem of the Nyquist, and so there is a general problem in radars, which is called the Doppler dilemma, okay? Which is essentially that you have two things that you have to be sure you want to do. You want to measure velocity, so you have this Nyquist issue, but you have also the problem that you want to have range and ambiguities. You have to sort out range and ambiguities, right? So, which means that you want to be sure that when you send a pulse and you start listening, you don't want to measure second three vectors or third three vectors, okay? So for the atmosphere, right, when you're looking at the atmosphere, you know that the atmosphere is maybe 20 kilometers thick in the worst case scenario. In the tropics, you may have clouds up to 20 kilometers. So you want to profile that atmosphere. So you know how much is the ambiguity that you want, okay? And on the other side, you have this Nyquist problem. And the two are, you have basically to do a trade-off between the two. Now, the advantage of this new technique, which is polarization diversity, is basically completely decouple the two problems. Why is that? Because you use polarization diversity to distinguish the signal. So when you send a pulse, okay, if you send a pulse with a single polarization, have a receiver in a single polarization, you send a pulse, you listen for a certain time, which is called the PRT, the pulse repetition time, then you send another pulse, okay, and you listen. But you are not able to distinguish between the two, right? Because they have the same polarization. But if you send a pulse in, let's say, a horizontal polarization, and then you send another pulse in the vertical polarization, then you are able to distinguish that at the receiver level. You just do a receiver where you receive H and B separately. So in that case, you can solve out this problem, okay? Okay, so basically, yes?
If you target the change the polarization?
Yes, I mean, of course, any technique has its drawbacks. Okay, and drawbacks is complications, and of course, crosstalk is a problem, yes, perfectly fair, but of course, crosstalk typically is small in atmospheric, for atmospheric targets, okay? So actually, the worst target that is producing crosstalk is the surface, okay? But typically, crosstalk of atmospheric targets is of the order of -20 dB. What does it mean, -20 dB? So this means that if I have a signal of 1 watts, 20 dB less means 0.01 watts. 20 dB is a factor of 100. Okay, so this is the typical crosstalk that we have. Okay, this causes a problem. I will sort it out. Okay. Okay, so basically in this long desert that we had from basically 2008 to the launch, we started looking at these things and trying to see, okay, what could be the next mission? Can we do the Doppler pattern? Okay, for the next mission. You have always to think forward, okay? And indeed, basically in 2017, I think if I remember well, we submitted the first proposal to this program, which is called the Earth Explorer program. Now, here you have all the satellites that ESA is responsible for. So there are and EUMETSAT, so there are the meteorology satellite, the Copernicus, and the science. So this is the core of this kind of missions here are the most important ones from the science point of view. They are the cutting edge kind of things. They try to explore new observation methods, new instruments. So here you see, of course, there is EarthCARE somewhere. In the days, Aerosol, yes, these were, already approved back in the days. Now EarthCARE was approved, I don't know, in 2003 maybe, I don't remember. Okay, so anyhow, how does it work? Well, it works like I always make the analogy with the Champions League. So you submit, every 2 or 3 years, there is a call, and basically open call from ESA. You submit a proposal. Typically, there are 20-25 submissions. They down select 4. Then 4 missions, they start doing what I call zero studies. So they do some industrial studies, plus they do some technology studies, plus they do some science studies. They do basically this phase 0 for a couple of years. Then there is the semi-final of the Champions League. So this means the 4 missions go to a meeting, they present all the missions, they debate, and 2 are selected. So we are exactly at this stage. So we have been down selected. So now this proposal that we have done, which is called this Wyvern mission, which I will explain what it is about, what it is about. We were down selected, and now we started last year phase A. Phase A goes on for 18 months. At the end of phase A, there is the final. Okay. So actually, instead of the Champions League, actually it's more. I would say it's better to make the analogy with the marathon. So we are indeed at the last 2 kilometers that, I mean, if you ever run a marathon, you know that they are the most difficult ones. Anyhow, so next year we will know if we are selected. So what is this mission about, this WIVER mission? WIVER stands for Wind Velocity Radar Nephoscope. So nephoscope was an instrument old in the Victorian ages. It was used essentially to track clouds to measure winds. Indeed, this is exactly what we are doing. So we want to use the clouds and the precipitation particles as the tracers of the movement of the winds. And what I want to convey today is simply the idea that, yes, this is a revolution. This is a completely new paradigm to EarthCARE. Because, of course, the big question is, you're just seeing another Doppler radar, is just a duplicate of EarthCARE. No, this is completely new. It's actually a revolution. Okay, why is it revolutionary? Revolutionary because of two things compared to EarthCARE. The first is that instead of just pointing nadir, we are doing conically scan. So I always say we are doing what GPM, VPR, what the GPM mission, the Global NASA JAXA Global Precipitation Mission, what precipitation radar has done for precipitation scanning. You can see these images if you Google the GPM radar. I don't know if you know GPM. Have you ever seen GPM flying over a hurricane? They map basically the three-dimensional precipitation structure of precipitation. Now we want to do this, the same thing for clouds. You've seen the difference. I mean, the key difference between a low-frequency radar like GPM, KU, KA, and a W-band, the key difference is that you can achieve a much better sensitivity at W-band. Okay, so we are seeing minus 35 dBz from EarthCARE, while then, with a little bit of integration time, we'll be at around minus 20-something dBz. Okay. Now, if you do you know what is the sensitivity of GPM? How many dBz? In fact, GPM can just detect the clouds, I mean, the rain that Pavlos was mentioning before. When there is light rain, yes, is where GPM can detect, but it cannot detect tough clouds precipitation, which is lower than that. So actually, the sensitivity is of the order of 12 dBz. The KA actually was supposed to have a little bit better, it's a little bit worse, 15 dBz. Okay, so this means that this guy here can really see the big stuff, the precipitation, the big particle, the big gas particles. But really, we cannot map all the clouds, all the cloud structure. This is what we want to do, and we want to do wide swath conically scanning mode. So we are scanning, so the satellite is in a polar orbiting, so it's moving at 7.6 kilometers per second on the ground track, and it's scanning 400 kilometer radius swath, so 800 kilometers, is doing a full turn every 5 seconds, so 12 revolutions per minute. So it's moving, so it's scanning quite fast. Now, yes?
So for a complete scan, you assume that the thing that it sees is the same.
It sees what it sees. Okay. So it is, I mean, I will show you in a second what the simulation of what it sees, but essentially it's making a turn, and after a turn, 5 seconds, is advancing. Of course, since it's moving at 7 kilometers per second, is advancing. The satellite is advancing 35 kilometers. So you keep seeing different stuff.
Okay.
Okay. So this is the first thing, the revolution, the fact that we are doing this wide swath, and I will iterate on this very much, because wide swath means much better sampling, and the sampling is a key word in the talk I'm giving here. Okay, better sampling allows you to do better science. Okay, even if you don't have a sensitivity which is as good as EarthCARE. Now that number, minus 15 dBz single pulse, this is a sensitivity of a single pulse. Okay, so if you send only a pulse, but then we know that we can integrate a little bit. Now the same number, if I look at the same number from EarthCARE, this is minus 21 dBz, single pulse, okay? EarthCARE achieves that amazing sensitivity because it's integrating a lot of pulses, sending a lot of pulse, okay? Okay, the other keyword is the polarization diversity. So the fact that we are doing Doppler, the other big innovation is that we are doing Doppler in a much different way. The fact that we are doing Doppler in that different way, as I said, allows us to decouple the unambiguous range problem from the Nyquist problem. In fact, we can achieve a Nyquist which is much, much better than EarthCARE, plus minus 40 meters per second. So this is indeed what allows us to measure horizontal winds. In fact, we are scanning an angle which is 42 degrees. So we are looking, of course, in our line of sight. Remember, when you do a Doppler measurement, you always do a measurement of the line of sight velocity, what you see in your line of sight, okay? So we will see something which is a combination of vertical velocities and horizontal velocity, okay? So this is the key measurement that basically this new technology enabled, okay? And in fact, this is key because on one side, we will see the three-dimensional mesoscale structure of cloud systems, which nobody can do on a global sense. And the second thing is that we can see really high winds in cloud system. Think about hurricanes or tropical cyclones. Yes, in terms of what we have at the moment, in terms of the wind observing systems, we have different things. This will be completely complementary. So we have, of course, measurements from geostationary. They just look at, from images from infrared or visible images. If you do just snapshots and you reconstruct the atmospheric motion vectors. You know, I think, Aerosol, because you are part of the Aerosol validation, so you know exactly what Aerosol has done. It takes this measurement of winds in clear sky, a little bit cloudy, but mainly clear sky configuration. Of course, all the aircrafts, when they take off and they land and when they measure winds. Radio soundings, yes, but all these measurements are, no real measurements in, first of all, yes, there are no real measurements in condition. Okay, cloudy precipitating system that we don't have really measurements apart from off-ground based. Now, why? And I go back to what Pavlos was saying about forecasts, right? So you want to do measurements. Sometimes when you do measurements, you do measurements mainly for two reasons. Either you want to understand processes and you want to understand models, parameterization, and so on and so forth, or you want to assimilate them and make better forecasts. Now, actually, the experience from Aerosol demonstrated that Aerosol was the most successful mission in terms of impact on the observations. So if you look at, you take an observation of Aerosol, that has the highest weight it contributes, let's say, has the best contribution in improving NWP. In fact, actually, ESA is now selling Aerosol. You know that there will be an Aerosol 2. Just because of that, okay? So because all the centers, DWD, CMWF, in Meteo France, they assimilate the real Aerosol data, and they actually prove that, okay?
By 1 week, they improve them so much that the 2 weeks after you have as good as before with Pavlos.
So you still have. So, in fact, actually, there was after all this success of Aerosol, there was a recommendation from the WMO to say, well, keep doing this, taking wind profiles. Of course, this is strong support to Aerosol too, but it's also strong support to this idea that we have in Aerosol. So, in fact, it was look at the complement. That is the synergy of all. What we want to aim at is to provide for the first time global observation of vertical structural winds in cloudy region, okay, cloudy precipitating region. So this would be the first step.
Will you be able to measure any precipitation at all?
And also in precipitation, yes, when of course we are not totally attenuated. When we have good signal, we will see also attenuation. We will see also winds. I will show in a second. So just to confirm this, Meteo France, now we're part of this phase 0 studies, Meteo France. So question is, of course, when you go to an agency, you want to sell an instrument, they will ask you, okay, what's the impact of these measurements, right? What is the additional gain that I get is from the observing the car, and actually they want actually to tell you what is the gain that you will have when you launch this mission, so in 2034, compared to the actual observing system that you will have at that time, right? So in fact, Meteo France is this study taking Aerosol 2 making, of course, they have their big data simulation machine where they assimilate everything. On top of that, they put Aeolus 2, and on top of that, they put Wyvern, okay, and simulate that.
So they put two Aerosol. So this is.
No, Aeolus 2 means that the Aeolus 2 is the Aeolus that is expected to fly in the 30s.
Then this will be twins.
Well, we did two, well, we did one instrument because we did one, the initial idea was 2035, Aeolus 2, the first one, A, let's say, and then there are two by in different periods. 10 years, they cover 10 years, but 5 years each, okay? So they do this thing, and they look at this reduction in the ensemble data simulation spread. Okay, this is a complicated thing, but anyhow, the meaning of this parameter is that if it decreases, okay, if it goes negative, means that you have a reduction in the spread, which is an indication that you will have a very good benefit from the assimilation. So you see, Aeolus 2 is the red curve. So a lot of the impact went in the upper troposphere and in the stratosphere, millibar. Sorry, hectopascal in the y-axis, right? If you take only Wyvern, is the blue line. Again, pushing towards the left impact. You see, graphically, visually, you see that the magnitude is similar to Aeolus 2. So this means that we expect Wyvern to have a similar impact to Aeolus 2. Okay, which is big because Aeolus 2 is already funded, but they are still struggling a little bit, but because it's kind of very, very expensive, becoming more expensive. Now, the key point here is that when you say, but I have already Aeolus 2, you could argue, right? Why do I need Wyvern? Because if you put them together, what you get is the green line. So they are completely complementary because you see, Wyvern, the blue one, is essentially making the most impact in the mid-troposphere. So they are very complementary measurements because, in fact, Aeolus is measuring winds in the sky. On the other hand, Wyvern is measuring winds in cloudy and precipitating conditions. So that, to me, is a very good case for an impact. Now, the other thing you can ask yourself is, well, this Explorer program is not about impact. It is also about impact, but it's about science. So one thing is, for instance, you can say, okay, can we do some science out of these measurements that we do, these snapshots that we get of this mesoscale system and the wind that we measure inside it? Remember, we measure line of sight winds. We don't measure the components of the wind, the vector, the wind vector, right? So the question is, well, can we understand a little bit better this? Well, indeed, what we have done is look at a little bit, for instance, tropical cyclones. Now, what we are doing here, this is a SEM model. This is simulation coming from actually Stony Brook University. So it's a global simulation. And this is a simulation of September 2017. There was Hurricane Irma, basically in the region of the Caribbean. So now the color here means blue means a lot of integrated cloud content. So of course, when there is dark blue means there are a lot of clouds. Okay. So remember, we measure winds in clouds. So we need the targets. We need enough sensitivity. We need enough return. And if we have enough return, if we have cloud precipitation, we will see Doppler and we can measure Doppler. Now you see what we're simulating here. We are simulating that the satellite is flying on an ascending orbit, and it's flying over them. It starts rotating, I start the rotation, and you see how it is rotating, advancing, and cutting through the hurricane system. And this is, now, imagine you are cutting through, so you are producing this length per thing. So imagine you have EarthCARE, right? But EarthCARE now, instead of being a straight thing, it will be a curved thing going around and cutting the hurricane. And this will be, of course, I could put the reflectivity, but here I just put the Doppler. Now you see, plus minus 60 meters per second, the Doppler, because I have this large Nyquist. And this will be signal coming from, as I go through the hurricane, you say, we'll see all these signals. So for instance, you clearly see when you cross the eye of the hurricane, imagine you have, of course, you have a cyclonic circulation around the hurricane. You see this you see now, you go up at a certain point, as you're passing through, you see you're passing through the hurricane, you pass from very negative to very positive because you are measuring line of sight winds. Okay? So you see the white line here is the freezing level. And this is essentially what we are plotting here is the winds only where we have targets with enough reflectivity. And I can tell you the number here is minus 18 dBz. So these are all the clouds exceeding minus 18 dBz. That will provide us a line of sight wind. You see how many winds we get? And especially in the part that is above the freezing level, above the line, we'll get a lot of wind. Why do you think that we will not get so many winds in the liquid part? The WS system. Right? So you will have, if there is a lot of rain in the hurricane, there are regions. Imagine that there are regions where there are quite a rain, but quite a cloudy region without not much rain. First of all, there is all the glaciated part. Then there are, of course, there is rain, but it's not raining like everywhere. Okay? Yes.
You said that we can measure up to 60 meters per second. But how much in clouds, how much you expect? What is the range that you
expect? I mean, think about, right? So actually that one, yes. I mean, the night which is plus minus 40, but once you have a night which is plus minus 40 meters per second, it's okay. In the sense, we will always be able to yes things. 40 meters per second, 40 times 3 is 140 kilometers per hour. Winds in a hurricane?
Yeah, I think.
I can get, I mean, depends on the strength of the hurricane, right? Hurricane. Okay, anyhow. I think I'm taking a lot of time here, but anyhow.
Leave the room.
But
we can continue from the location we are going.
Okay, anyhow, if you stop, I mean, okay. So actually, you say, well, I don't believe your simulations about the hurricane. You probably did something tricky and so on and so forth. So we did a different study here. This is what Frederick did. We have CloudSat. So CloudSat, actually, there is a nice data set built by CSU, the Colorado State University, where they say, okay, let's take the 15 or 17-year record of CloudSat. And the CloudSat flew over several tropical cyclones. Okay? And there are, in fact, if you look at the CloudSat webpage, they don't show warm rain, they don't show ice clouds. They will show all these pictures of the overpass of the hurricane because these are the most, appealing one, right? So what we did was the following. Now, CloudSat is a 94 gigahertz. So this is a real reflectivity measured by an instrument. So these are the values that are real, okay? So the only thing that you have to change with Wyvern is to put in the slant geometry. So the slant geometry, what does it mean? Is that you add a little bit of attenuation. That's it. Okay, so you can reconstruct. Okay, for instance, this is an overpass of whatever Choi 1 Typhoon. Okay, and from the view of CloudSat, you reconstruct the view of Wyvern. And we were very conservative, saying, well, if there is attenuation in the region where it's raining, like we take it out. We don't want to count it. Okay, we want to be sure that we are not really going into the region of massive attenuation. But you see the kind of values, the kind of wind profiles that we will get, okay? We will get a very nice idea of what's going on in terms of circulation inside the hurricane. But the key is that we have a very large Nyquist, and this is enabled by this technology. So this is statistical, we say. Now you have a problem here, right? Because you are, compared to CloudSat, you have less sensitivity. Your instrument is less sensitive. First issue, right? So you will see less clouds. And the second thing is that you will have attenuation. So you will lose something because of attenuation, the extra attenuation that you have because of the slant path. And how much do we lose? So we computed how much we do lose using, say, okay, we know how much we see from CloudSat, how much of the tropical cyclones we see, okay? How much do we lose? So here the touchstone is CloudSat. Okay, and we are trying to see what is the fraction. So in that case, for instance, the black line, sorry, the gray line is how many profiles per year CloudSat sees in tropical cyclones. And you see the curves are how much you see, of course less, you will see less. if you have attenuation, the slant attenuation, the black, with the same sensitivity of clouds, or if you lose attenuation, or if you lose sensitivity, if you go from minus 30 dBz, which is the sensitivity of clouds, to sensitivity which are less than that. So you lose something. But still you have plenty of winds there, okay? In particular for the winds, okay, the winds is a rule of thumb always. The winds will produce decent results. This is true for wiring, this is true for EarthCARE, when the signal to noise ratio is larger than 0 dB. So this has, you have to compute with single pulse. Okay, for EarthCARE, minus 21 dBz. So if you imagine you have your signal from EarthCARE, you see the reflectivity, you can think, okay, I will see a decent Doppler, not in all the pictures that I see, but only when the reflectivity exceeds minus 21 dBz. Same thing for Wyvern. The threshold for Wyvern is minus 18 dBz. Okay? So this is the number of things in proportion, you see. Compared to CloudSat, we think we will get a decent Doppler in 50% of the profiles. So if CloudSat sees something in my tropical cycle, I can imagine enough of that, I will measure a very good wind. But now, what is the advantage? Well, the advantage is that, yes, I lose something because I have less sensitivity, but I gain immensely in what? Well, if you think about this, imagine that you have your tropical cyclones, the circle, let's say is circular, with a radius of whatever, a diameter of 1,000 kilometers. Now you see the cyan line is a possible overpass of EarthCARE or CloudSat. And if the satellite is the same, look at what Wyvern will do. Instead of just getting this curtain, which is the cyan one, we get all those ones. So we'll have much better sampling. So I lose, I measure 50% potentially of what the CloudSat sees, but I have the advantage of much better sampling. So order of magnitude, for winds, we think we will see 32 times what CloudSat actually sees. And for clouds, the sensitivity, you don't need to go to the SNR larger than 0, but you can dig a little bit in to be of the order of 50 times. So this means that we will have an immense number of measurements, for instance, in tropical cyclones. But the same applies for windstorms in the Atlantic, polar lows, and so on and so forth. Now, this, of course, means that we will have a lot of winds, line of sight winds that we can give to the data simulation center. So here, this will answer the fact that, well, hopefully, this will improve the numerical weather prediction also for this very important system like tropical cyclones and so forth, right? But there is another question here. The other question is, well, I told you so far, Doppler measurements is always line of sight, right? If the policeman, right, has his radar, it's the same thing, right? The policemen, some of them, they have these devices which are based on Doppler radar, right? If you are going towards the policeman or away from the policeman, that direction will find you if you are exceeding your speed. But if you are passing that way, okay, in that direction, you will not see any Doppler. Measure zero velocity. If you are going 200 kilometers per hour that way, you will not see it because we will measure the line of sight velocity, right? So now the question is, can I do something instead of the line of sight? I don't understand the line of sight. In fact, when I was showing you the plot before, right? When it was passing over the cyclonic center, we were seeing all this change in sign. What is that? I don't understand. You understand wind with vectors, right? So you understand the wind vector. So the question here is, this is the scan of Wyvern. So you have always a forward scan and a backward scan. So this means that if you look at a specific point or a specific region, you may have a look, for instance, for this region, you will have looks from these directions and looks from these directions. So this means that you will measure the line of sight wind in this direction, the line of sight of wind in this direction. So if these two directions are independent, you can actually retrieve the full horizontal wind. So the horizontal, the U and the V component, the meridional, so the zonal and the meridional component. Of course, you see that this will depend on where you are in the swarm. Because for instance, if you are here, so you are exactly corresponding to the ground track. So the satellite is flying in this direction, is scanning in this direction. Now, in that direction, suppose that it's going from south to north, I see, when I'm looking forward, that point, I measure the line of sight in this direction, which is the meridional component. When I am here and I'm like this, I will measure this component. This is still the meridional. So in this part of the swath, in the central part, I will only be able to measure the meridional part. But in the other part of the swath, I can do the retrieval of the full. Of course, if you have clouds, if I have targets, I need to have targets, I need to have the tracers. Anyhow, so we did a study, try to retrieve the thing. This is kind of the ballpark values that we have for instance, for the hurricane that I simulated before. So for the meridional, more or less the result is independent of the distance from the satellite track of the order of 3 meters per second, which is a good value. We are retrieving that meridional component within 3 meters per second. You see that the U field, so the zonal, it goes to 3 meters per second when you are far away, but it's much bigger when you are close to the ground track. Now, this is about winds so far. I have shown you that we think we will have very good impacts on manual weather prediction. This has been, Meteo France has now consolidated the study doing an OSSI. And we think also that we can use the snapshot that we have to understand better the dynamics inside tropical cyclones or any meteorological systems of interest. Now, why also this is important for cloud and precipitation products, the sampling? Why this is a revolution compared to CloudSat and compared to EarthCARE? Well, again, I show you, this is a paper from Graham-Stevens, 10 years of CloudSat findings, blah, 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 right? It shows this plot here. Actually, this is not from Graham-Stevens. This is a snowfall statistics from Mark Cooley. But CloudSat has been used and has been, it is currently deemed as the best instrument for producing snow climatology. In fact, actually, I can tell you that before CloudSat, we didn't know how much snow was falling in the polar regions. Actually, it was completely missing from the Earth energy budget. Precipitation has to equal evaporation relative to energy. Okay, so there was this part of the precipitation, so the polar precipitation was completely missing from the, you typically see this Earth radiation budget annual mean in the IPCC report was missing. Okay, so this was. CloudSat was discovered that well, there is snow and actually quantify how much snow there is. And indeed, this is the snowfall climatology at 1.1 degree based on 10 years of CloudSat data. Now, what do you see there? What do you see in this? Of course, you see, first of all, yes, you see that there is a lot of snow in the Southern Ocean. There is this part of Greenland which has a lot of snow. But what else do you see? What do you see in this picture? Still, if you look at the details, red, yellow, green, do you think that this is real? Or not? Yes. Yes, exactly. So we are trying to do a climatology at 1.1 degree, even if we have 10 years of overpasses. Yes. That's the difficulty of Alval. Okay, you wait forever for this satellite to pass on top of your head. Okay, that's the problem. Okay, in fact, when I say, "Ah, we put Alval in maybe 2 years," you will not do any Alval in 2 years because you don't have statistics to collect essentially to sample the phenomenon. Okay, now, and this, in fact, this is the paper from Graham-Stevens. Now, this is, Graham-Stevens is saying, okay, let's have a look at the snowfall rate over, not at 1.1 degree, but we want just to see the full continent of Antarctica. Okay? And I look, yes?
Okay, let's make a poll, because that's a poll, and then we continue. plans. I keep this in mind, keep them. Just a very few of us, we can let you stay here, we'll just go upstairs. And keep it fantastic, thanks for class. That's what I do. Whatever. They have the book, the place for this time.
Okay, so anyhow, the bottom line here is, again, in the plot, if I probably start this from the beginning, but I was showing actually now another flight of simulating another flight of Wyvern over Antarctica, over the Southern Ocean. Again, you will have this swab, and you will sample 50 times, roughly, better than CloudSat. So instead of waiting for 50 years, collecting data for 50 years, you will never have. You just get the same thing in 1 year. Instead of waiting for 50 months, it's just 1 month.
The overpass, so will it go lower? Supplement will go lower than the supplement because the roads lower.
No. So also the ground track will move extremely fast. Okay, so the ground track will move. In fact, if you think about you are illuminating a region, which is a sub-kilometer region also for Wyvern. It will move 500 kilometers per second, very fast. In fact, that's why the reflectivity will not be as accurate as yes. Okay, now there is a sensitivity issue, but there is also a noise due to the fact that you are not integrating many pulses.